Video, I want to introduce the basketball problem, show how to get the solution analytically, and how to use simulation in R to hopefully validate, at least show the plausibility of the hand computation that we're going to do. So here's the situation. You've got person 1 and person 2, and they're going to alternate shooting baskets, starting with person 1. Okay, it's known somehow that person 1 has a 1/3 probability of making their shot, and person 2 has a 1/4 probability of making their shot. And these probabilities are with us for the entire problem. They don't change, and an important thing to note is that they certainly, person 1 making a basket doesn't depend on anything that's happened with person 2 and vice versa. So these are considered independent probabilities. So the question is, what is the probability that person 1 is going to be the first person to make their shot? So that's our scenario. Okay. So we want to start tackling this thing. So the way I started thinking about it is to say, well, what are the different ways that this could actually happen? So they head out to the basketball court, person 1 picks up the basketball, and they shoot, and they score! Okay, well, in that case, the trial would be over. Person 1 would have made their shot, game over. And the probability of that happening would just be 1/3, because that's the probability of person 1 making a basket. Okay, so suppose that didn't happen. How else could person 1 win at this little game? Well, suppose person 1 missed, and then person 2 missed, and then person 1 made their shot. Okay, so we're going to call that event 2, or A2. And the way that you would compute that probability is fairly straightforward. We have independent events occurring, so we can just multiply the probabilities. So this 2/3 represents the person 1 missing their first shot, and then person 2 had to miss their shot, which is 1 minus the probability of their making their shot, which was 1/4. So we've got 2/3 times 3/4. And then the last thing that has to happen in this and series of events is person 1 would have to make their shot, which happens with 1/3 probability. Okay, what else could happen? Suppose that didn't happen. You could have a situation where person 1 misses, person 2 misses, person 1 misses, person 2 misses, and then person 1 makes their shot. And so how would you get that probability? Well, now we've got the 2/3, the person 1 missing, happening twice, so you have to multiply it twice. 3/4 happening twice, and then this final make. Okay. So I'm claiming that the probability that we're after should be like the union of all of these different events, A1, A2, A3, onward to, in this case, infinity. Because although it becomes ever less likely, the likelihood of this happening becomes vanishingly small as you proceed through your trials. There's really no limit. They could both, in theory, just go on missing forever. I mean, that's not going to happen, but that's like, if you can't just draw an arbitrary end to it and say, well, if person 1 hasn't made their shot first by 100 shots in, we're going to call it a day and go home. No, like in theory, that could go on forever. So I claim that this is the beast that we're after. To make a generalization which is very convenient. Okay, so if I start to write out what's happening in A3, 1/3, 2/3, 2/3, 3/4, 3/4, what we can see is that we can actually perform a cancellation. Okay, this 3 will cancel this 3 will cancel this 3, and if this was A4, we would just have 3 of these, and the 3 3s would cancel with the 3 3s in the denominator. In any case, what we'd be left with is 2/4, or a half, and that's getting multiplied times a half. So in this case, we'd have 1/2 squared. So my claim is that we can write that the probability of AN is equal to 1/3, which is that final make by person 1, times 1/2 to the n minus 1, which sort of represents the combined missing of both parties up until that point. Okay, so hopefully I've been explicit enough about how I've come to this, and we can move on. Okay, so to get into the theory of why I make that claim a bit, like A1, A2, ... up to A infinity, potentially, these are disjoint events. And the reason I'm confident saying that is because, you know, there's no way that two of these things could happen, you know, for a given experiment. You know, if on the third round person one makes their shot, you know, that's the end, and there's only like one way that could happen, and you couldn't have a case where you went to another round, but in the last round the person won because you would have stopped doing the experiment. So these are disjoint events. And it follows from the third axiom of probability that the probability of the union of these events from 1 to infinity is equal to the sum of their individual probabilities. So all we have to do is evaluate this piece that I came up with. I mean, I want this to be the probability that we're after. So how can we start chugging through this summation? And, well, to start with, the 1/3 term doesn't involve the n. It's a constant in the summation, which means we can take it out of the summation and multiply it times whatever we get at the end. Okay, so I'm going to let s be the sum that we're after, just to like make it a concise variable so I don't have to keep writing all of this. So let's write out like what's actually happening. S is equal to, well, 1/2 to the n minus 1. When n is 1, n minus 1 is 0. 1/2 to the 0 is just 1, plus 1/2 to the 2 minus 1 is 1/2 infinitely. So here's the big trick in how to solve this thing, is you get in there and you multiply both sides by 2. And when you do that, you get 2s is equal to, well, 1 times 2 is 2, plus 1/2 times 2 is 1, plus 1/4 times 2 is 1/2. And what you see is that the way that we originally defined s, we get s again in the expression. Okay, so we can simplify and just write that 2s is equal to 2 plus s. And using a little bit of algebra, you just solve that and you see that s is equal to 2. So the probability we're after in the basketball question is, drumroll please, it's 1/3 times 2, or 2/3. Okay, now is there any way that we can demonstrate that this is so? Using a simulation. So what I want to do is I want to simulate like 10,000 such experiments. And I should probably offer before I continue that there's probably easier, more elegant ways to do this. This was just sort of on first pass what I came up with as a sensible way to simulate this. Okay, so I'm creating an output vector to load the results of our simulation into. I said I wanted to do 10,000 trials. So I've got a replicating sequence of zeros, 10,000 elements long, that's going to be holding our output. Okay, so for each trial, I should say, in 1 to 10,000, I want the following, all of the following stuff wants to happen. Okay, I want to simulate person 1 taking 100 shots. And you might say, well, why go with 100? You know, what if they kept missing over and over and over again? And I'm gonna suggest that that's probably not going to happen, and that if they have a 1/3 chance of making their shot, somewhere in their first 100 shots, they're going to make a shot. And I'm happy enough, you could, for the purposes of this simulation, that's what I'm going with. Okay. What do I have here? Okay, so you could imagine that on creating these random variates, you're going to get some kind of chain of like 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 1, 1. You're going to get 100 of these, right? And what I'm concerned with is where person 1 is having their successes. So I'm asking which elements of this vector are equal to 1, because of the results being 1s and 0s. Okay, so then I've got a vector of the indexes of where the person has made shots. So it might look something like 2, 5, 26, 99, and then there's nothing after that. So just that would be if they had very few successes. But that's the index of where they had the success. Okay, and so where they had their first success then, very obviously, is just the first element of that vector. Okay, if their first success was on their 10th shot, we would have something in this vector. We would have 10 as the first element of this vector. And so that's what I'm interested in getting. Okay, person 2, we're going to sort of represent their shots in the same way as Bernoulli trial random variates. I want 100 of them, this time with their probability of making a shot of 1/4. Okay, so what have I done here? I said early trials is person 2 indexed from 1 to person 1's first success minus 1. Okay, and here's the reason why I've done that. Suppose that person 1 made their 4th shot. Okay, if they made their 4th shot, what I'm interested in looking at is the first 3 shots of person 2. Now, when I'm looking at those 3 shots, if any of them was a success, I would say that that person, if any of those trials was a success, then person 2 would have like won this little shooting contest. And so that would not count towards the chances of person 1 having the first success, if that makes any sense. Okay, so basically for this whole thing to count as a success, as for person 1 being the first person to score, we would want early trials of person 2 to all be 0. Okay, and that's the big step here. And the reason it's minus 1 is because if person 1 made their 4th shot, we don't want to allow person 2 to make their 4th shot. The game is over, so we're only concerned with the first 3 shots. Okay, so I call this next guy here, did person 2 win, is going to be a sum of their own early trials. And then what I want to do is I want to look at that sum, and if it's equal to 0, I want my big output, my output through these 10,000 trials to get a 1, and if not, I want it to get a 0. Okay? So after I do that, I should then have a vector 10,000 elements long of 1s and 0s. If person 1 was the first person to score, there should be a 1. If person 2 scored before person 1, there should be a 0. And so then it should simply be a matter of taking the sum of that vector, dividing it by its length, and that should give us the proportion over these 10,000 trials of when the proportion of times that person 1 did make the shot first. Okay? So I'm going to copy my little simulation here. I'm going to drop it in R. I can run the simulation again. 0.6675 is even closer to 2/3, and I'll just do it a third time for good measure. 0.657, that one was a little under. And one last time. Okay, so hopefully I've convinced whoever's watching this that the computational, the analytical solution to this basketball problem agrees very well with the long-run probabilities that we arrive at by using R to simulate the situation. Okay, thank you very much.